Okay, so let's start today class. Today we are going to discuss about the three-phase induction motor, rotor current, rotor EMF, and power. Okay, so let's try to see how we can find the rotor current and rotor induced EMF. As you know that the equation of EMF induced in the motor is similar, induction motor is similar to the EMF induced in the transformer. Okay, so just we try to first of all share the screen and then we will continue our discussion. So, okay, so just today we are going to discuss uh, rotor EMF, current, and power of the three-phase induction motor. Rotor EMF induced, EMF induced current and power, current and power of three-phase induction motor, three-phase induction motor. Okay. So we already explained the operating principle of three-phase induction motor, how they can try to rotate of their rotor. Okay. So as well as the comparison from the transformer and three-phase induction motor. So at a standstill, the relative speed between rotating magnetic field and the rotor conductor is synchronous speed, that is ns. Okay. So under this condition, let the per phase generated EMF in rotor circuit be E2. Okay. At a standstill. So that means at a standstill, standstill standstill, the relative speed between the relative speed between rotating magnetic field and rotor conductor, between rotating magnetic field, rotating magnetic field and rotor conductor is synchronous speed ns, and rotor conductor is synchronous speed ns, is synchronous speed, that means represented by small ns, that means revolution per second, revolution per second, that means ns revolution per second. Under this condition, let the per phase generated EMF in the rotor circuit be E2. Under this condition, let the per phase generated EMF, let the per phase generated EMF per phase generated EMF BE2 presented by E2 and E1 is the generated EMF in the stator winding. Okay, so this one is your E2 when the rotor speed is say 0.4 ns, when the rotor speed is say 0.4 ns, zero point 0.4 ns, slip is rotor speed is this one, the slip is how much? Slip is 0.6. Already defined this slip in the previous class. So slip is 0.6. That is nothing but difference of synchronous speed minus rotor speed to the synchronous speed. Okay, so 0.6 and the relative speed speed between rotating field field and rotor conductor is 0.6 ns and rotor conductor is 0.6 ns is 0.6 ns zero point 0.6 ns zero point 0.6 ns under this condition the per phase generated EMF becomes under this condition the per phase generated EMF becomes generated EMF becomes 0.6 ns into E2 by ns. That means 0.6 E2 is not. So 0.6 ns 0.6 ns into E2 0.6 ns into E2 divided by ns. That means equal to 0.6 E2. 0.6 E2. So what we observe that at the standstill, the rotor EMF induced is represented by E2, and if rotor is rotate at any speed, particular speed, then rotor EMF induced will becomes whatever the product of slip and EMF induced E2. Okay, so you have to keep in mind when you deal the three-phase induction motor, rotor EMF induced, that is nothing but product of the slip. Okay, slip is nothing but change in the ratio of change in the synchronous speed minus rotor speed divided by synchronous speed. Okay, so whatever the value of slip at a particular rotating speed of the rotor is the multiplied by the E2. Okay, so in general way we can write here the rotor EMF induced at any slip is represented by, suppose that S, then rotor EMF is equal to S into E2, is it not? So for if you want to write for any slip S, okay, so therefore the per phase generated EMF under this condition in general for any slip S, in general any slip, any value of slip, any value of slip is the per phase generated EMF in rotor conductor is equal to the per phase generated EMF in rotor conductor is equal to SE2 conductor is equal to SE2. SE2 As you know that the value of E2, that means EMF induced in the rotor winding, that is nothing but is E2 is equal to S. You know that the EMF induced of the rotor coil, that means root 2 pi F1, root 2 pi F1 to phi F1 KW2 N2 phi F1 KW2 is your winding factor of the rotor coil. So that is represented by KW2 winding factor of rotor coil into number of turns of the rotor coil into flux per average value of flux per pole. That means phi. Okay. So N2 is your number of turns of the rotor coil, number of turns of the rotor coil into flux, that is represented by phi. Okay. So this one we can represent root 2 pi S into F1. Just write together slip and frequency, rotor frequency F1, so supply frequency F1. Okay. So just root 2 pi root 2 pi SF1 S F1 into KW2 into N2 phi, not KW2, that means winding factor KW2 into average flux per pole, that is represented by phi. Okay. So that means we simply write the rotor EMF at any slip AC SE2. Okay. Now rotor leakage reactance, so that how we can represent, that means XL equal to rotor leakage reactance omega L not. So 2 pi F omega can be replaced by 2 pi F into L. So now rotor leakage reactance equal to omega L, that means 2 pi F into L. So can be represent this way. Okay. Omega L maybe right omega can be replaced by 2 pi F, that means 2 pi F rotor frequency. If here that means rotor frequency, that means represented by rotor frequency by F2. So just F2 right here. F2 into L is not into L. So this SF1 can be replaced as F2. You know, this SF1 is your rotor frequency F2. That means EMF induced is your root 2 pi F2 kW2 into phi. Similarly here rotor frequency is replaced denoted by F2. So 2 pi F2 into L. Okay. This is at stainless steel. Okay, at stainless steel. So rotor leakage reactance at a stainless steel can be represented just simply this 2 pi F2 L2 equal to X2. Okay. So rotor leakage reactance, rotor leakage reactance at a stainless steel at a stainless steel equal to 2 pi F2 L2 equal to X2 at a stainless steel pay, this frequency becomes F1. Okay, so 2 pi F1 L, it's right here, equal to 2 pi F1 2 pi F1 into L2, or you may be represent as a small letter of inductance, that means L2 matter is equal to X2 at a stainless steel. So what is the leakage reactance, rotor leakage reactance at any slip S? That is simply just multiply by the slip here. Okay. So this one becomes this one X2. Okay. So rotor leakage reactance at any slip S rotor leakage reactance rotor leakage reactance at any slip S is equal to 2 pi F2L is equal to 2 pi F2L F2 L2 Okay, so you know that how we can represent the rotor frequency in terms of stator field supply frequency, that is nothing but product of the slip into supply frequency. Okay, so this one if you write here SF1 in place of F2, then just simplify this equation 2 pi F 2 pi F 2 pi F1 2 pi slip S into F1 1 into L2 equal to S x2 S x2 x2 1. Okay. So now rotor leakage impedance, what is the value of rotor leakage impedance at a standstill and rotor leakage impedance at any slip S. So let's represent their value. Rotor leakage impedance at a standstill, rotor leakage impedance leakage impedance at a standstill speed is equal to square root of R2 square plus X2 square. Or we can represent their impedance value. That means square root of R2 square, that is resistance square, plus X2 square, that means reactance square. So instead square root of R2 square plus X2 square X2 square. So at any slip S, rotor leakage impedance can be represented at any slip S, at any slip S, rotor leakage impedance equal to rotor leakage impedance that is equal to square root of R2 square plus what is the value of leakage reactance Sx2 at any slip S. So just put here Sx2 in place of x2. So equal to square root of R2 square plus S x x2 whole square plus S x2 whole square x2 whole square. So per phase generated EMF divided by the, now just see how we can find out the rotor current. And we know that EMF induced divided by impedance. Okay. So just put here the value of per phase generated EMF per phase generated EMF EMF divided by the per phase rotor leakage impedance divided by the per phase rotor leakage impedance by the per phase rotor leakage impedance rotor leakage impedance gives the per phase rotor current gives the per phase rotor current per phase rotor current so per phase current at a standstill how we can represent that means EMF induced divided by impedance so per phase current at a standstill still that is equal to E2 by that is the voltage EMF induced divided by impedance standstill so just E2 divided by impedance of standstill that means the square root of R2 square plus X2 square you know so just R2 square square plus X2 square plus X2 square per phase rotor current at any slip S is given by how much? That means only change the terms of here. This one is your E2. You know, this one is your EMF induced of the rotor. E2. This one is your E2. So per phase rotor current at any slip S is given by per phase current rotor current rotor current rotor current at any slip S is given by at any slip S is given by is given by I2 equal to presented by EMF induced at the rotor speed is some at any slip S. So that means just rotor current replaced by represented by I2 equal to ratio of EMF induced at any slip pace divided by impedance at any slip pace. Okay, so this one is represented by how much? AC2 is E2 divided by the square root of R2 square plus SX2 square. So R2 square R2 square plus SX2 whole square plus SX2 whole square. If you simplify this equation, you may write E2 divided by R2 by S whole square plus X2 square. Okay. So if you simplify this equation, just we write E2 by square root of R2 by S whole square is whole square plus X2 square plus X2 square square. So this is the value of rotor current at any slip S. That means E2 divided by R2 square root of R2 by S whole square plus X2 square. Okay. Now if we so there the circuit diagram equivalent of rotor circuit, that means the current of I2 source is your E2 and total impedance of the circuit is your R2 by S whole square plus X2 square. Okay. So what is the equivalent circuit of the rotor? We can draw it's like and then we will just try to find out the value of power of the rotor circuit. Okay. So you always kept in your mind the rotor leakage reactance is represented by SX2 and EMF induced at any slip is represented by SE2, and then we just simplify the equation of current, that means EMF induced by impedance at any slip S. So you will get something like this one. Okay, now we just try to draw the equivalent circuit of the rotor, and then we will just find the how much power input in the rotor circuit from the stator side. Okay, so we will discuss the equivalent circuit the next class. So just we stop here and